Good morning, everybody. I'm Reshef Tenne from the Weizmann Institute. And first of all, I would ask you to turn off your cellular phones. We have a list of 3 distinguished speakers, and I'm very pleased to chair this session. And I think that the best thing that we could do is to move to this hall, because yesterday the projection was not great. And at least now I can read very well the slides, which is a big advantage. Anyhow, it's a great pleasure to chair this session. And the first speaker needs no words to describe him. Professor Rudy Marcus from Caltech. Just thinking of the Marcus theory, in my past I did some electrochemistry and kinetic theory of matter, and everywhere you went, you met the Marcus theory. And I recall the days many years ago when in the community of photoelectrochemists, I was doing photoelectrochemistry. The first proof for the Marcus theory, for the Marcus charge transfer, kinetics, was accepted with a great respect. And this was probably the end of the 80s or early 90s. So the Marcus theory here's the person, the pioneer that did the Marcus theory of charge transfer. And I think with all his many contributions, many contribution and important contribution, the Marcus theory stands out as an enormous intellectual achievement. And the amazing thing is that if you go to the website of Rudy Marcus, which I did, you see papers that are so relevant to modern science, like perovskite solar cells, theory of perovskite solar cells, theory of nanocrystals. So he's like an old wine. He's getting better and better with time. So with no further words, Rudy, the floor is yours. 45 minutes, please.
Okay. Well, thank you very much. It's a real pleasure to be here and to participate in the celebration of the 70th anniversary of the State of Israel. I remember it well. I was a young man then. Of course, like most of you, I'm still a young man now. All right. Well, today I'd like to talk about a number of themes. In the past, looking at the past, physical chemistry consisted of lots of equations. I'll give a few examples. Of course, in the past 30, 40 years, there's been a switch to computers. And to treat certain problems, computers are definitely the way of doing it. Analytical theory has its limitations, and so on. And the question, though, is there some middle ground for treating complex phenomena? In other words, if there are no simple equations available, is there nevertheless some compromise that involves the use of some equations to treat part of the problem, and then that suggests what to do with computers? You've broken down the problem into component parts. So in addition to talking about molecular motors, I would also like to address that question. All right, let's see if my old experimental days can come back and I can see how to use this machine here. Yeah, all right. If you think back to, well, most of you aren't old enough. If you think back to the 1850s, around that time, beginning onward, and in fact before Boyle's law goes back to the 1600s, there are lots of equations developed to treat all sorts of phenomena that we as chemists, particularly we as physical chemists, treated in the laboratory. So that was the name of the game. And here are many examples, and there are lots more, covering all sorts of fields, ranging from various thermodynamic properties to thermodynamics itself, what a glorious set of equations it is, to kinetics of various kinds. But now the experiments are increasingly demanding, increasingly detailed, and theory is, for certain things, is not as simple as one had hoped, like electronic structure. And so computers have played an increasing and an important role. And one of the questions I'll try to address is a kind of a middle ground which bridges the two, which relates the two, which uses analytical theory to bring out certain problems which are then tackled by computers instead of solving it all at once. All right, if I may go back to electron transfers, because we'll start with those equations and we'll see how one might be able to apply equations like that, not exactly like that, to molecular motors, which have nothing to do with electron transfers. Okay, now let's see. Yeah. All right. The modern electron transfer field began in the late 40s when people studied isotopic exchange reactions. Isotopic exchange reactions were widely studied because there were so many different kinds of radioactive isotopes that became available to act as tracers for these studies. These self-exchange electron transfer reactions are, in a sense, the simplest reaction in all of chemistry because no bonds are broken or formed, just an electron transfer. And it was because of that kind of simplicity and thinking about what the requirements are for the electron to occur without violating law of conservation of energy that led to relatively simple approximate equations for treating the electron transfer problem. So the fact that we didn't have to calculate detailed breaking and forming of bonds in the simple electron transfer meant that we could use other things, interactions of ions with each other, with solvent, non-equilibrium solvation, various things like that we could bring in and get some sort of answers. And this is a depiction of the electron transfer reaction. Because of time, I won't try to go into it, but the main thing is that you go from one set of charges to another set of charges. These triangles are intended to be oriented water molecules around there. It's a purely descriptive thing. They're more highly oriented around the more highly charged ion. So that has to change. If you tried to have the electron jump before it would change, you'd be formed in a wrong environment. You'd violate the law of conservation of energy. In fact, there was realization of that when I saw this famous paper of Bill Libby, that it was great to apply the Frank-Compton principle, but then I realized it's violating the law of conservation of energy. So you have to get reorganization, something happening before the electron transfer, and then you can match the energies and so on. One is dealing here with many coordinates, of course, many solvent coordinates. Let's say 10 to the 23rd. But it's hard to draw a picture with 10 to the 23rd coordinates. So what one customarily does in statistical mechanics, and applied to this problem too, is go over to a statistical description whereby you try to take into account everything, and you end up with a calculation, say, of free energies. So it was possible to reduce the problem to one of calculating free energies of non-equilibrium systems. These going from, let me see if I can get this thing right here. Going from here to there is the electron transfer, but all sorts of solvent fluctuations have to occur in order to permit one to reach this region, this intersection region here. Okay. Well, anyways, there are all sorts of details with that. There's a way of defining a reaction coordinate such that even in the 10 to the 23rd dimensional space, you can pick out one coordinate, not an orientation, not a bond breaking, nor happens to be an energy difference coordinate, and you can use that to describe the whole reaction and to describe the free energy as a function of that. Those are all details that, of course, we won't try to go into here. And here are these parabolas. There's much that one could say about them. Here's a parabola for the reactants. let me see if I can just get this thing here. Here's the parabola of the products. You start around here in this reaction, this complicated reaction coordinate space. You end up around there. To do that, you have to reach here, which is a 10 to the 23rd minus 1 dimensional intersection in molecular space, and then you can go. So you have to calculate fluctuations, and that's what the theory was all about. And if you boil it down without putting in what the specific quantities are, this equation here for the rate constant emerged as a function of the driving force of the reaction. That's a standard free energy reaction. As a matter of this, depending on this reorganizational parameter, how much of the bonds have to change, how much of the reorientation has to occur. There are expressions of the theory for each of those things. So that was the equation. And it was derived for electron transfer, and there are all sorts of consequences because there's a similar equation for electrode phenomena, and you can try to relate the two, and so on. And also you could relate with this equation rate constants of what's called cross reactions, two different kind of redox systems with the respective isotopic exchange rate constant for this system, the isotopic rate constant for that system, and the equilibrium constant. You could derive a relation between them. There's an advantage in doing that just generally in theory, because the more you can obtain an equation where you have symbols like this, and you have some expression for what they are, you have symbols like this, you notice these symbols here don't have the specific properties of the reactants or the solvent there. There's no dielectric constant that appears as a lambda. It appears in lambda and so on. So if you get an equation which contains quantities that don't explicitly write out the specific properties, then you may have a theory that's more general than the one you derived from. And that has turned out to be the case, actually. I found in the course of writing several successive electron transfer papers, I could keep on generalizing and generalizing and generalizing in ways that, I enjoyed. And anyways, we did. Now, this was derived for electron transfer. And you'd think that experimentalists would be smart. They wouldn't apply it to something which isn't electron transfer. But Norman Sutton applied the equation, this equation, or really something related to it, the cross-reaction equation, to a reaction which really involved an atom transfer. And it worked. And then the equation was also applied with another problem. This is by Lewis, J.N. Lewis's son, who's at Rice, applied to another problem, namely the transfer of a methyl cation from one aryl sulfonate to another. He could get the self-exchange rates, he could get the rate constant, he could get the equilibrium constant. He could test an equation that was derived from the one that I showed there. And here is an example. There's the calculated value here, and there's the experimental value here for different aryl sulfonates. And here are the experimental points. There isn't a single adjustable parameter there. The fact that the points lie on the line is a test of the equation that I showed, or test of the equation applied to cross reactions. And then in another application, here is a theoretical computation, again of a methyl cation transfer, but a different one. And this is by Wolf and Mitchell. I know Wolf. Yeah. And here is the, this is taken from their paper. This is the calculated barrier by the theory. This is the one that they obtained by computation. This straight line, the points are the points for each. The straight line is the theoretical line. So the bottom line for these two things and for others is that sometimes you obtain an equation. If that equation is free from writing out the specific parameter dependence of the quantities, you may have an equation that is more general than what you started off to have. And these are examples in point. Now, more results. Now, you know, you can't get away from them. Of course, one may wonder, why is it that an equation that was derived for electron transfer with the cusp there, the intersection thing, applied, why does it apply to a reaction which has no cusp? It's just sort of a smooth potential. I mean, that's what a methyl cation transfer or an H transfer or what have you involve. And so I set up a simple model using what's called the bond energy, bond order model, in part due to Linus Pauling. And I simplified that and applied it, and then came out many years ago, this is 1968, with this equation for the free energy barrier. And you notice that the first two terms are identical with those for electron transfer. The third term is somewhat different, but it's different because in electron transfer, because of the topography, you can get what's called the inverted region. Whereas if you just transfer a bulk particle from one to the other, it just goes, the more downhill it is, the faster it goes instead of becoming slower. So there is no inverted region, and indeed in this equation there is no inverted region. But there is a certain similarity. The main thing is that using that approximate quadratic equation applied to things that have nothing to do with electron transfer, where it's been applied, it works. And so it occurred to us that maybe we could go one step further. Maybe we could try to apply to a problem which wasn't even a chemical reaction. Now, how might we apply to a problem that wasn't a chemical? Like, for example, suppose you consider a molecular motor, which I will show in a moment, where ATP, adenosine triphosphate, goes into the motor and eventually comes out in some other form. It goes into a pocket, a cleft. As it goes into that, bonds begin to close on it. And in a sense, you have a bond-breaking, bond-forming process, but this time of hydrogen bonds and other kinds of bonds like that. So maybe for some of the processes that occur in the motor, we might be able to apply this equation and see how well it works. All right, let's go to the molecular motors. Here is a biolayer membrane. Here is the photosynthetic reaction center, for which there was a prize. Here is this ATPase that I'm going to be talking about, or at least I'm going to be talking about a part of it, for which there were several prizes. Well, in fact, in all of this membrane, it shows how fortunate the biologists are, biochemists are. There are 4 or maybe even 5 Nobel Prizes in there. But anyways, so what I'm going to talk about is this part of this ATPase here, largely because there are now lots of different kinds of single molecule experiments on this ATPase, and of a quantitative nature, experiments that one never dreamed of when many of us were young. And so I'd like to see how we can apply the theory to steps in there and see if there's some way that we can take the data and see if we can predict some data from other data without any adjustable parameters. So that's the goal, okay? I'm very allergic to adjustable parameters because in the old days, to fit a rate constant, one often adjusted parameters and so on, and that's not a very satisfying. I mean, I didn't, but anyways, it was done, and that's not very satisfying. All right, so let's turn to a molecular motor, and this is from Walker, who got the Nobel Prize for part of the structure here. And what it shows is this membrane. Let me see if I get this thing work. Here's this bilayer membrane. Here's the part that's sticking out. That's the part in which there have been so many single molecule experiments that we're going to talk about. And here's the motor in action. There's a proton, a place where protons can go in. There's a very clever acid-base reaction inside, which pulls one part of the system towards another, causes it to rotate. That rotation is hooked to some axis that I'm going to show a little bit more of, and which is highly asymmetric. This asymmetric axis applied to various subunits that are attached to it causes them to open and close. When they open, they permit something to go in. When they close, they permit something to react, and so on. And you have a molecular motor that is associated with a chemical reaction. This is a sort of a description of it. And here's where the proton on one side of the double layer comes in and attracts an anion group, and that causes a rotation. Eventually, the proton goes around and comes out the other end. Here's where this part here, from here up, is the part that's been studied so much in single molecule experiments. This part has recently been studied in cryo-EM. So there'll be more work on that. All right, so I would like to talk about processes going on here. This is a cross-section. This is that asymmetric rotor, which on pressing against various parts causes them to open and close, causes the ATP, well, the ATP goes in from the outside, from the liquid in there, and as this thing is rotating, it closes, or the ATP itself will help close it by the binding, and that causes something else to open, and in this case, an ADP comes out when that opens. Anyways, there's a concerted, more or less concerted kind of motion where reactions are going on. And the question is, the key question is, how can we treat those systems? How can we treat the mechanics? And how can we treat the chemistry? And how can we combine the two so that we have a working type of theory? Well, let me just summarize some of the single molecule experiments. There's what's called stalling experiments. This is where, by magnetic means, you cause the rotor, you actually force the rotor to go through a certain angle, and then after definite times, you release it and either goes forward or backward, and from that you get rate constants. So that's one kind of experiment. Another is controlled rotation experiments, whereby you force by a magnet this to attach to, something that is magnetic that you can rotate. You force it to go round and round, and you look and see what's happening. You detect the species there by fluorescence. There are special conditions you work under, and so on. But the main thing is an independent kind of experiment. And there's what's called free rotation experiments, where it just rotates freely. And there are also free rotation experiments now whereby instead of milliseconds, which is a usual time scale, they've arranged it so they can study things in microseconds. And when you have that, it turns out you can't use rate constants to describe it. You have to use time evolution of a different kind, and we're working on that also. All right. Here's one point to perhaps try to make, namely that if you take this ATPase and you stick it on a slide and you do some measurements like rate of hydrolysis, the results are only meaningful if that agrees with the system which is not constrained in that way. And the fact that these lines here essentially overlap says that, fine, everything's okay from that point of view. This is sort of trying to give a description of, here's this little motor here. Here's something you attach to it. You can cause that to rotate to different angles. When you do that, you change the free energy of the products relative to that of reactants. You start at one point where the reactants are more stable. When you go to a different angle, it's the products that are more stable. And the idea is to somehow bring that into the rate expressions. All right. How shall we combine the chemistry and the mechanics? I mean, what should we do? I mean, we can't just write down mechanics plus chemistry equals motor. What should we do? So let me show you what we did. And I hate to put down equations because they're more interesting things for many. But the main thing is that here's a rate constant, which depends on the angle of rotation. There's a free energy barrier. The free energy barrier has this kind of chemical term in it. Well, really, the chemical term it really consists of several things. There's the chemical part. Here's the part which is related to the motion part, the mechanical part. So the way of bringing in, combining the mechanics and the chemistry is by having equations which deal with the mechanics, namely the fluctuations of the angle about one sort of stable point, and later on the system has another stable point. The fluctuations around there, those fluctuations give you the mechanical part, and the usual expression gives you the chemical part. Anyways, you put them together and you try to make predictions. Now, how can we make predictions without any adjustable parameters? What can we do? Well, there are different kinds of experiments. So we can try to take some experiments and see if from those experiments we can make predictions about other experiments with no adjustable parameters. We'll try that. May work, may not work. If it doesn't work, you go back to square one. Fine. Many of us have been at square one for longer than we remember. But anyway. All right. So here are the results with no adjustable parameters. The points here, this is for binding of ATP and dissociation of ATP from one of those pockets. Here, the points are the experimental points. The lines are the theoretical lines with no adjustable parameters. So what's worked here is that we've used data from other single molecule experiments that are independent of these to calculate quantities that appear in this kind of experiment. And this is the kind of agreement. Now, this is for one step. This is for the, in this case, an ATP going in and binding and non-binding coming out, the equilibrium constant, and so on. We've done that for the other steps in the process, and you have to link them together. And I'll just show one slide here, which is just intended to give the scope of the thing. There's a full 360 degrees involved. So we were focused here in the previous thing just on one part of the process. But there are multiple steps going on in different parts of the process. And a year or two ago, Shander Volkenkasko, who's been, he and I have done this work together, published a paper that when you take into account not only one process, but something happening later on in another process, how do you link the two so that eventually you get a complete theory of the whole 360 degrees? So the theory for that is in a paper in PNAS a year or so ago. And the question is, what data are there? Well, it turns out there are data from Kadashi and others in Japan. And that data was never published, only the statement that there are data available, because there was no way of interpreting the experiments at the time. And since then, Adachi has sent to Shandor the raw data, and as soon as we can get to it, we'll apply this the analysis, which I've not showed. How do you link one thing to another? We call it long-time events and so on. And we'll see how well it works. There's no guarantee that it'll work because, you know, you take it one step at a time. All right. Where do we go from here? Well, first let me say something about work that we're doing now. But the group is very small, so the pace that we're going at is slower than that of a snail. I don't know how fast the snail moves, but this is going a bit slower than that. But first, there's the coupling of subsequent events. Okay, we published the theory of that. We have to apply it to these experimental data that was provided to us. Then there's work of the type that I haven't described, where they're studying it under special conditions that you see changes going on in the microsecond range. All that we've been talking about there is the millisecond range. And there you can't use rate constants. You have to use equations that give things as a function of time, and whether it's Langevin equation or Fokker-Planck equation, I mean, there are two approaches. So anyways, we're trying to do that now. And then we're embarking on a third theme, namely that based on the analysis of which I described much of it here, several co-workers have now set up the expression for the molecular dynamics guided by what we found, and we'll see how well that works. I mean, for example, the question is, if you let the molecular dynamics run for at least a little bit, will you, as a result of the process going on, see an opening or see a closing going on? That is yet to be seen without forcing the opening and closing. But this is the field of rotary motors. In a sense, rotary motors are simpler than linear motors. There are far many linear motors, you know, kinase and myosin and so on. The rotary motor is very compact. Something goes up, something goes down, you know, closes, opens, very compact. Whereas when you have these linear motions, you have an arm walking along a track and maybe hunting a little bit, and so on. It's a much more loosely packed thing. So we started on that. We hope to, we're in the process of writing a paper. We're writing a paper before we know the results. And we'll see how that works out. But the main point there is that what I've tried to describe here is a way of trying to relate complex phenomenon by not necessarily calculating everything ab initio, but trying to see whether you can take the set of experiments and sort them out so that you can see relations between them. To the extent that you can, to the extent that your predictions work out, it means that you've understood something about it, and that surely will help with a organized, detailed molecular dynamics calculation. You're looking for very specific things now because of the underlying theory. And we hope that that'll work out, of course. Well, it's been a pleasure to be here and to try to give some idea of trying to bridge the gap between equations on one hand and models and detailed, complicated systems, of which this is a beginning. Thank you.
Thank you, Rudy, for this wonderful talk.
Thank you.
And I'm sure there will be comments and questions. So, the discussion is open. Please.
So I'm just confused about one thing. In these rotary motors, where does the angular momentum come from in the initial chemical reaction?
Oh, yeah. In some of these experiments, they're kind of stalling experiments, right?
Well,
in
nature.
In the actual system, and in this microsecond type of experiment, where does the angular momentum come from? There's a lot that I could say. I'll just try to say it briefly. We think that the part dealing with the angular momentum is in the so-called undamped region in applications, say, of Fokker-Planck, and the part dealing with the diffusion in and out of the process is in the damped region. So we have equations that both together, one of which undamped and underdamped. Now, something going in and causing something to close will change an angle, and whether that provides the... well, one thing we do know in these very short time experiments, that the way they do the experiments, they have a long waiting time, and then an event happens, And the system goes from 0 angular momentum up to a finite value in, I don't know, I think it was 10 microseconds, a little bit further. And what's happening there is a chemical process is occurring. And that process, coupled with the opening or closing of things, is sort of transferring, that's what we believe, is transferring it to produce the angular momentum. But the main thing is that for the actual system, where the thing is rotating like that, just discussing in terms of rate constants won't do it. You have to have that angular part velocity, which we have in the form of a Fokker-Planck. And we've yet to put all those details together and see how that comes. But I think, short answer to your question, I think it comes from an opening and closing, or opening, closing, a change in one rotational part which causes the thing to rotate. And indeed, when we set up a model for that, a Fokker-Planck equation, which we have for variables, the angle, the angular velocity, and the penetration or other process of an ATP into it. When we set up equations for that, the ATP penetration being overdamped and the others being underdamped, then indeed we get an immediate jump in velocity from that. So I think it's coming from this process of something going in or something going out in that, and the effect on opening and closing.
Okay. Do you mind if please, afterwards, Aida.
How do you take into account the hydrolysis of ATP that I saw you have there?
Pardon?
How do you take into account the hydrolysis of ATP?
You mean the ATP going to ADP?
Right.
Yeah. We do that by having essentially applying those quadratic equations. In other words, so far the main thing we've got is the ATP going in and so on. But the hydrolysis part, that part, we would do it in essentially that way. That just like you have, the equation has been applied to bond breaking, bond forming, then we'd have here for the hydrolysis. You're breaking some bonds, you're forming other bonds, and I mean, that's what we would use. In other words, we would use a similar formalism and see how well it works out.
Aida, please.
This is kind of philosophical question. At some level of complexity, this very insightful relationship might not tell you what is happening, and if you compare it to simulation, I mean, there is a level where, while you could use this equation for interpolation, it will not be able to distinguish between different possibilities. Like, for example, if it's completely overdamp or underdamp, there is one extra dimension. So what is your opinion on this?
Well, I think on the underdamped and overdamped thing, yes, the only way we could treat this thing going round and round and round in the actual motor was to treat that motion as underdamped. Because it's not a diffusional motion, you see. The ATP coming in and out, or ADP going out, or what have you, may be a diffusional motion. But this thing going round and round and round, a diffusional motion for the round and round would be little back and forth, diffuse, etc., not going round and round and round. So that's why in the results that I haven't shown here, why in setting up the equation for that microsecond type of experiment, we use underdamped for that angular velocity, the angular motion, and we used overdamped for the diffusional thing. So it's a combined thing.
Okay, but if you go to molecular model, you might find that there are more larger dimensionalities, yet it's actually overdamped. I mean, there are questions which are very...
Yeah, well, you know, Arya, we take these things one at a time. We take a step forward. If the step fails, we're the first one to move back and try something else. So you know, from our point of view, and it's true in so many things we've been interested in, it's exploratory. And we try to be flexible, and sometimes it works. Yeah.
Please, Fraser.
Thank you, Rudy. Could I raise the question that you have used your equations for the intake of ATP and the hydrolysis to ADP plus inorganic phosphate? What about the reverse process?
Yes, we use them. Yes,
with,
absolutely.
How do your equations stand up when you're doing the ADP plus phosphorus to ATP?
Well, in order to study that, or the studies of that, where you're forming ATP, is that what you're saying? Yes. Yeah. The experiments typically dealing with that, are experiments where you have the combined F1 that we're treating and the F naught below. So that involves how is the proton motion that's going related to the coupling, which is related to the other. And here, Junge, in a review article, made a major contribution, and I believe that Area made a major contribution. That's a problem that we haven't tackled yet, but I mean, it's certainly one that you know, we're very much interested in, but you know, one thing at a time. But it's a good point, yeah.
Yeah, please.
In this very interesting analysis of equations that are valid beyond the realm in which they are obtained, of course, you suggested an extension of it through a specific model, this bond order type of treatment. My question is the following. Since then, we see a lot of treatment, microscopic treatments and simulations, at least of simple problems such as electron transfer. Do these simulations give us insight as to why these expressions, why these parameters are so universal beyond the specific regime?
I think it's more of confirmation. In other words, to presume that the free energy, which is related to displacement times the force and so on, and hence it's quadratic in displacement, or at least in a parameter there, that was a hope that the free energy would indeed be a parabola. And various computations, which don't assume that, by David Chandler, by Tom Miller, have indeed found parabolas, you see. So if one were to try to put it in a broader context and say, okay, well, how can I theoretically get a parabola out of this and so on, both statistical mechanics? One would use something like what Area used in a distribution. You do it in terms of cumulative things. You expand the exponential, you stop at the second term, you've got your parabola and so on. So one would look into why is the next terms, why are they small, you see? I mean, I think one would put it in that context to get a deeper understanding. No, I was absolutely amazed that, that things worked out. Because I mean, this was the simplest model of what I was doing, you know, linear approximation for relating electric fields of polarization. No guarantee that it was going to work, but it was a simple thing to do. And, you know, you try it. And I certainly wasn't thinking in terms of it being applicable to all sorts of systems. I was just trying to struggle to learn things, that's all.
I may have missed this in your answer to Paul Brummer's question, but where do you get the symmetry breaking? Where do you get the unidirectional motion from?
Oh. The actual system, if you look at that gamma thing, is asymmetric. So it may spring from there. That's one thing I haven't gone into. I haven't thought about it, but it's a very good question. But the whole thing has an asymmetry to it, built into it. That gamma thing, that gamma subunit that sticks up, is not cylindrically symmetrical. It's definitely asymmetric. So there's a built-in asymmetry there.
But that's not in your equation.
Pardon?
That's not in your equations.
No, no, that's right. That's right. I mean, that, to do that, you'd have to bring in structural things. Absolutely, absolutely. This is saying, given something, what do you find? Yeah.
Please, Shimon.
Not a direct question, just to pay tribute to Paul Boyer, who passed away yesterday. Which I think was absolutely remarkable. Many years before Walker's crystal structure or Kinoshita single molecule experiment was able by simple biochemistry experiments to predict that this is a rotary motor.
No, absolutely. He had the three thing. No, absolutely. The tripole thing. Absolutely, yeah. Now, mind you, having said that, as a chemist, in the early days when I was looking into Oxford meetings and trying to understand it and gave up on it, I looked at Paul Boyer's equations, not his equations, his papers, and not being versed in that language, I found it very difficult to understand. But other people understand it. Certainly the Nobel Committee understood it well enough to give me the Nobel Prize.
Okay, one last question, please.
Okay, actually, this is a little bit philosophical, but since you started on this essentially note, so, I mean, the question, you started this talk by essentially saying that analytical methods are not sufficient.
I'm sorry, I can't hear you.
You started this talk by mentioning that there are complex problems for which purely analytical methods are not sufficient. And then you have to have this kind of mixture of analytical and perhaps simulations and other things.
Yeah.
Arias Barcel's reaction was that some problems may be even more complicated than that, and you have to solve them purely by simulations. However, now we are facing an even more extreme possibility, which the deep learning people are telling us that you don't have to essentially even simulate the system. You can just basically put in some data, get some answer, I don't know, 5, and that's all you can learn about this system. So, I mean, but the question is it, I mean, do you find it?
Well, that might satisfy some. I don't think that information where you put something in and get something out would satisfy many. One wants to understand.
Right. I mean, it actually satisfies, from discussions I have, most biologists.
Yeah, well, then that's fine. I mean, that's fine. I mean, we all are satisfied in different ways. Some of us want to try to understand and are not just content to see. I mean, it's great to have the results there, okay? That's great. But we're not just content to see results or to know that we can reproduce them by a complicated model. One would like to have enough understanding of a phenomenon that if some new results come out from something, one doesn't necessarily have to go to a computer to see, well, the trends, will it go this way or that way? One has enough insight that one can then, I mean, that's the hope at least anyway.
Okay, I think with that we shall complete this discussion, beautiful and amazing discussion. And we thank so much Rudy Marcus for being able to join us and give this splendid talk.